Thanks, Jan, and thanks very much to the organizers for this great program, workshop, and conference. And yes, I want to talk about scattering gravitational waves of spinning black holes. That's not what I've drawn a picture of here. This is a picture of what everyone knows is the context for this workshop: binary black hole, say, two black holes moving in a bound orbit or scattering, whatever, and they emit gravitational waves. So why do I want to talk about scattering gravitational waves off black holes? What does that have to do with this problem? I'll get there in a moment. And just some notation, which we've seen many times before. These two black holes are going to have some masses, and I'm going to be focusing on their spin. Most of this talk about spin, which we call S. I really mean the intrinsic angular momentum, which is useful to think of, right, as the mass of the black hole times its so-called ring radius. I'll just abbreviate that, ring radius, because it is in a very real sense. The spin, intrinsic angular momentum divided by the mass, is in a very real sense, which I hope we'll also get to. The radius of the ring singularity, which is hidden behind the horizon of the black hole. And I'm saying here, the fields of classical GR and amplitudes and their interminglings are pushing from many complementary directions toward higher orders in spin and higher multipoles. Let me emphasize, for example, the spin, in a way, as we have just seen, in angular momentum is in a sense the gravitational dipole moment of the system. The next most important is a black hole, for example, has a quadrupole moment that roughly goes like its mass times this ring radius squared. So this is because it's spinning, it's oblate. That's why these aren't spheres, they're ellipsoids, these horizons, for example. So this quadrupole moment proportional to spin squared is the first in an infinite tower of multipole moments that even just a stationary black hole has when it's spinning, as opposed to when it's non-spinning, it just has a monopole, it's spherically symmetric and no higher multipoles. So these spin effects and higher multipole effects, these are what I'm particularly interested in this talk. And I want to go to very high orders in spin. And so the field is pushing from complementary directions toward higher orders in spin and higher multipoles for useful descriptions of the dynamics of binary black holes. We could also talk about neutron stars instead of just black holes. I might mention something about that later, but particularly interested in black holes in the post-Newtonian, post-Minkowskian, and self-force expansions, which I hope by this point in the conference need no further explanation. And I'm listing here some very recent works, all of which have something to do with spin. And my standard for higher orders is like spin cube, fourth, fifth at this point. And from many different approaches, for example, post-Newtonian effective field theory. I believe we'll hear much more about this afternoon from Michelle. And I have this long list of references, all from within the past 2.5 years. I'm not going to say much about many of them, except some really exciting, very recent work, which is pushing at the second post-Minkowskian order past a very interesting boundary and answering a problem that's a few years old now, going back to some work which very conjecturally was claiming it could calculate for two black hole scattering, the aligned spin black hole scattering angle to all orders in spin at linear order in G and up to fourth order in spin at G squared. So this is a result that Alfredo and Alex and I put out in December. By the way, these are the first 4 digits of the archive number. So that's December 2018. that guy. And I'll try to explain a bit how we got this result. It was very conjectural at the time. And I will mention some about how these very recent works. I should also mention this very recent work, which all three of those, in a way that I'm not going to talk about at all. Well, so first there was this very important work by, sorry, it's that one. Chen, Chung, Huang, and Kim, which went to the same levels, let's say g squared s to the fourth, for generic, not just aligned spins. I know many of you are familiar, but just to say, when black holes in a binary are spinning, of course, in general, they could have generic spin directions. The motion gets much more complicated leading to what we've heard in other talks is referred to as precession of the orbital plane when the spins are not aligned. But a very simple case is the so-called aligned spin case, which is what I'm looking at down here. When the spins are in the same direction, that direction is orthogonal to the plane of scattering. In a sense, the degrees of freedom there are the same as in the non-spinning case. So it's a very simple problem. The spins just appear as extra parameters. And just to say a few more words about that setup. So here, I'm looking down on the plane of scattering. Say I have, and I'm looking again at actually a special case of this problem, which is where I have a curved background and what I'm going to call a probe or test spinning black hole, which is an object that has a finite ring radius, but negligible mass, if that limit makes sense. And I want to claim that limit does make sense to a very, very large extent. And it's a very interesting limit. And I hope to say more about that later. But this result, which was put out claiming that this very simple formula here gives you the scattering angle for binary black hole scattering to these orders. Notice this extremely simple form at first post-Minkowskian order to all orders in the spin. So A is the ring radius of the big curved black hole down here, sigma. So this is actually the result in the probe limit that I was just discussing. This very simple structure at first post-Minkowskian order, quite simple also at second order. To all orders, here it was all orders in both spins. Here we can go to all orders in the spin or spin per mass or ring radius of the big black hole, but not the little guy. That was the limitation. So for the spin or the ring radius of the little black hole, there's a problem with going beyond fourth order in spin. Okay, and where did this result come from? Well, it went back to these two papers. Let me focus on, well, this first paper by Alfredo was stressing that even with perhaps with high orders in spin, a two black hole, so black holes come in, black holes go out, scattering process through order g squared, at least the important parts of it can be described by a scattering amplitude, and the important parts of that scattering amplitude really only consist of these three contributions. These are actually, they're not Feynman diagrams, they're unitarity cuts. And let me also mention here this mass scaling, which basically implies that we get the complete first and second post-Minkowskian order results for arbitrary mass ratios from this at least spinning probe limit, like I was talking about, because in good ways of organizing the calculation, let's say that part is the probe limit. So apart from, every term has this factor of g times the two masses, these two terms at one loop or g squared order, here and here, have an extra power of one of the masses, okay? But you can see these diagrams are essentially the same. They're mirror images of each other. In the probe limit, if we say M2 is much smaller than M1 and go all the way in that limit, we lose this third diagram. And in the probe limit, we just get, say, these two. And this corresponds to this answer for the scattering angle that we were looking at up there for this probe guy in this Kerr background. Okay, but to recover the full information, right, the non-trivial information is actually there. It's just you take this order g squared part up there and exchange the identities of the two bodies, right? So whereas here we had a symmetric dependence on the ring radii of the two guys, here you can see it's anti-symmetric between ring radius of big guy A and ring radius of little guy sigma. But that all of the information in this term that we're missing in the probe limit on that side is in the term that we have in the probe limit. So I'm reiterating this claim that up to second post-Minkowskian order g squared, all of the information is in the probe limit, even with spin and seemingly to all orders in spin. Okay, more about what Alfredo started putting together using building block amplitudes from Arkani, Hamed, Huang, and Huang. That's this paper right here. So Alfredo built his unitarity cuts, which I'm drawing up here, the tree level one graviton exchange, the one loop triangle cuts from basic building blocks that were discussed by Nima et al., which are, so, I said these are cuts for the amplitudes people, but they're built out of, you can see just two basic building blocks, a 3-point amplitude and this 4-point, which we see, for example, here, that 3-point amplitude, or here, and a 4-point Compton amplitude, so-called 4-point, because it looks like if these were electrons and photons, that would be Compton scattering. So that's why we call it the Compton amplitude, but here instead of electrons and photons, it's black holes, spinning black holes and gravitons. So this 3-point amplitude, which was originally discussed by Arkani Hamed et al. And used by Alfredo to build these unitarity cuts. Let me just say, roughly speaking, it's when you have spin on the black hole, that's this A parameter, it's the same answer as without spin times e to the momentum of the graviton dot the ring radius vector. So the ring radius vector is just, it has magnitude of the ring radius and it points in the direction of the spin. And this, you might, that's kind of in Fourier space. It's like e to the I spin per mass or ring radius dot a derivative, if you will. And that's, if you think about acting on some field, say the gravitational field, that's, if you will, translating x goes to x plus IA, like shifting the position of the particle off into the complex plane by an amount of I times this length A that is part of the Newman-Janus way of understanding a Kerr black hole. is that a Kerr black hole is kind of like a Schwarzschild black hole, except you translated it off into complex land by an amount IA. And this has been understood in many different ways in many papers. In the meantime, okay, that second building block for building unitarity cuts to describe black hole processes is this Compton amplitude, which was also discussed. How can you write down a Compton amplitude for, so this 3-point amplitude in this original paper by Nima et al. Was understood for massive arbitrary spin quantum particles meeting a graviton. But for this 2 gravitons, the Compton amplitude, they wrote down an answer only up to spin 2. And it's related to the fact that massive higher spin particles with spin quantum number greater than 2 have problems. But let me say, in the meantime, in particular, I want to point to this paper by, where is it? Aude. Actually, I don't have it. No, it's here. By Raphael and Andreas, who are in the audience, and Case, who is not here. A way of taking that original amplitude from Arkani Hamed et al. And better understanding it, and in particular writing it in this very nice form. For the non-experts, I'll just very briefly say these are spinor helicity variables when you write a null momentum for a graviton as a product of 2 spinors. These are the objects that appear here. I really just want to stress that there's a formula that makes a lot of sense. It's in fact another exponential, kind of like that exponential, makes a lot of sense up to the 4th order in the spin, but not beyond. And let me point out a feature that this object here, if you expand the exponential to 4th order in A, you see this object, you'll have, say, go up to 5th order, you'll have 5 powers of this downstairs. It will cancel these 4 powers of that same object right there, and you have the so-called spurious pole. Again, this is related to problems with massive higher spins greater than 2. Let me also point out, in this classical answer for a scattering angle, there's also a manifestation of this spurious pole. If I take this formula that we conjectured is good up to 4th order in spin, if I just extended this formula, if I just put a 5 there and took the next term, you can see actually I also have some kind of pole, even in this classical scattering angle, coming into the denominator. That is very much an echo of the spurious pole in the Compton amplitude. Okay, and so the question, the 2 main questions that I want to answer, even though I've already taken 2/3 of my time, this is kind of the intro. Okay, these amplitudes came from really like thin air. They're supposed to have nice properties. They're supposed to have a well-behaved high energy limit, a uniquely well-behaved high energy limit. That's where they came from in the first place. They seem to make sense, don't have any obvious problems up to spin to the 4th, but do those amplitudes and do these answers for scattering angles that we derive from amplitudes, does this actually describe black holes? I haven't addressed that at all yet. And in fact, I would say even this work here, which did the same thing, instead of aligned spin scattering angles, they did generic spins. For that matter, also these works, which I hoped to say more about, but I'm pretty obviously not going to have time. They focus on, I'm sorry, not the, yeah, these 2. They focus on even more nice structures which come from a completely amplitudes type perspective. Nice amplitudes, nice unique looking properties of amplitudes that seem to single out. These amplitudes are probably the ones describing black holes, right? But all of that, back to Alfredo and our paper here, all of this is just conjecture. Right? You can have nice amplitudes with nice properties, but can you show that they actually have anything to do with black holes? So there was a lot of work looking at that, for example, in this paper, but that was only up to spin squared. And at spin cubed, spin to the fourth, even where we thought we had answers, and these guys also have it for generic spins, not just aligned, it's conjecture. You've got to connect to actual black hole physics somehow. Okay. And yeah, I wanted to tell you more about, so effective descriptions of black holes. For example, I was mentioning massive spin-F QFT Lagrangians, or even just Ansätze or bootstrapping for these Compton amplitudes for massive higher spin particles, or purely classical world line action descriptions of, let's say, effective black holes, or attempts at describing effective black holes. How can we actually connect them to black hole physics? So at the level of the 3-point amplitude, there's a very nice story where you can connect, and essentially, like at linear order in G, and to all orders in the spins, which let me just say, why do I want all orders and spins? Well, if we can, it sounds great. We want to resum the whole thing, so anything that we can resum, let's do it. Like post-Minkowskian versus post-Newtonian. There is a very nice story about connecting any of these things, any such effective descriptions, at the level of the 3-point amplitude to the linearized stationary Kerr solution. I wanted to tell you some about that story, but I think I'm going to have to skip some of that. But if we wanted to figure out, like, going to G squared, where at least in the unitarity approach, an important ingredient is this Compton amplitude. So we can also try to connect, I mean, we have to insert, well, so for example, the work of Baron et al. Starts from their massive spin as QFT Lagrangian. They compute a Compton amplitude. They go on to plug that Compton into the triangle cuts, etc. But how do we see that the Compton amplitude coming from a QFT Lagrangian with certain parameters, Wilson coefficients in that Lagrangian, how do we know that corresponds to black holes? Can we connect it, say, is like Kerr at G squared instead of Kerr at G? Is that enough? I think the answer is absolutely not. We have to connect this to perturbations of Kerr, to solutions of the Tucholsky equation, which basically, let's just say it's the equation that describes linear gravitational perturbations of Kerr. Now, there was some previous work, like instead of directly looking at this simpler building block, the Compton amplitude, like looking at the two black hole process, and let me say usual self-force calculations. So a little point particle in orbit around a big Kerr. So these computing something to do with that situation is something that our friends in the self-force community routinely do. For example, they compute the so-called redshift invariant and the precession frequency invariant for a small particle in an equatorial, in an orbit in the equatorial plane of a background Kerr spacetime. And there was a paper here where we looked at comparing via this magical first law of spinning binary mechanics, comparing predictions from amplitudes with these self-force calculations. Again, but that's at the level of this two black hole process. So can you do some black hole perturbation calculation that directly connects to the Compton? And so my claim, I'm finally explaining the title of my talk, which is, okay, even just looking at this Compton amplitude, it looks like graviton comes in, meets black hole, graviton comes out, and of course, black hole is still there. So that's what I'm saying. This is, maybe this has something to do with classically scattering gravitational waves off a black hole. And the claim, our claim, so we started looking at this in this paper last August with Fabian, Alfredo, and Chris. But in the paper that's out, we just did a scalar toy model. So scalar waves scattering off Kerr. Of course, the real problem that we want to do is gravitational waves scattering off Kerr. We hope to have a paper about that very soon. And I'm skipping the linearized Kerr story. I wanted to say a lot of, and not to mention root Kerr. But okay, in my 2 to 3 minutes, I want to make one more point. So I hope I motivated why we want to look at solving for linear perturbations of Kerr. That's solving the Tucholsky equation. Specifically, we send in a gravitational plane wave, incident from infinity, if you will. It interacts with the Kerr black hole and waves come out in all directions. We want the amplitude of the scattered waves. That's going to be a function just of these parameters gm, this ring radius a of the Kerr black hole. The frequency of the incoming wave, 1 over its wavelength. And otherwise, it only depends on some angles. The angle between the incoming wave vector and the spin, and then the 2 angles between the outgoing wave vector and the coordinate system set up by those first 2 vectors. This can be done. You can set up boundary conditions corresponding to an incident plane wave. You can solve the Tucholsky equation. You can get an answer for this amplitude. It looks like this. It has the remarkable property. All right, and so what is the small parameter, the expansion that we're doing? We are assuming that lambda is much bigger than these 2 length scales, gm and a. So that gm omega is a small parameter. Also, a omega is a small parameter. Remarkably, at the first 5, through the first 5 orders in omega, the answer is a polynomial in these 2 small parameters, gm omega and a omega. That certainly didn't have to be the case. And the tree level Compton amplitude, so tree level means like linear in G, but we hope, we dream that this thing will make sense to all orders in A at linear order in G. It's sitting right here up to this level. We pick it off, and let me just tell you, very long story short, that part, it does indeed match those amplitudes. If you interpret them correctly in a classical limit, we get a perfect match to these amplitudes that came from Nima et al. As I would say best rewritten and interpreted most directly to make this link that I'm talking about with the classical amplitude here by Oda, Haddad, and Helicity. We get a perfect match if we're doing it right. Of course, our goal, though, was to use this Tucholsky solution to go beyond where they couldn't go to the next order and pick out, okay, a omega to the 5th, gm omega. All right, but here's where we run into big problems. And maybe it's not surprising, we run into problems exactly where the amplitudes run into problems. At the next order in omega, this Tucholsky answer is no longer just polynomial in these small parameters. By the way, the coefficients that I'm omitting, they only depend on these three angles that I was mentioning. In fact, they're also polynomial in sines and cosines of half of those angles, apart from some overall factor which represents the physical pole at forward scattering. Okay, suddenly, where we had hoped to pick off this guy, we run into non-polynomial things. For example, this log of something, or this digamma. So digamma of z is gamma prime of z over gamma z. And so I'm 2 minutes over, Chair. Should I? Can I maybe take 3 more minutes? Okay. What do we do with this? Okay, we wanted, should we expand in something, these functions now to get, can we pick off this part that we wanted if we expand, for example, in A over GM? Is that what we want to do? That definitely is not what we want to do. In fact, you will get such a term if you do that, but you will get all higher orders in A at the same order in frequency, which makes it look like our whole paradigm is breaking down. That's not what we want to do. In fact, even though it wasn't clear to me for a long time, it now seems much more clear, and thanks to Chris Kavanaugh in our collaboration for pointing this out, we want to make this expansion, right? Post-Minkowskian, we said we're looking at post-Minkowskian. We want to expand in G at fixed A. And I hoped for this to motivate this with a story about how linearized Kerr works. And how linearized, let me just say, linearized Kerr is very much a naked ring singularity with radius A. But yeah, I simply don't have time to talk about this. Please ask me about it if you want to know more. But in this post-Minkowskian regime, when you expand in G, if you take Kerr itself and expand in G, at linear order in G, you get this very much naked ring singularity thing. So what we want to do is probably, I mean, almost certainly, if there's any hope of getting a Compton amplitude at linear order in G to all orders in A, we want to make this expansion. Okay, but we have a problem. I mean, in fact, you can do that expansion to these answers. You get some issues. Notice these weird functions, this log, this digamma, they have problems exactly when A equals GM. So that's the so-called extremal case. For example, this log, it's real when A is less than GM, but it becomes imaginary when A is bigger than GM. Similar things happen with this digamma function. Okay, but we hoped to take these answers and analytically continue beyond. So the actual problem that we solved was there was a horizon. It is a sub-extremal black hole. So, and we wanted to analytically continue to this super extremal naked singularity case. But there are choices of branch cuts in these functions. And it's unclear what to do. And probably really what we need to think about is, does it even make sense? Can we solve the problem actually solving for perturbations of a naked ring singularity? And that sounds like a nice idea, but I have no idea how to do that or set up the boundary conditions. But these are the things that I wanted to mention, and interested to hear about ideas that anyone might have about any of the things I said. And thanks very much for listening.
Thank you, Justin. So, David, why don't you start?
Yeah, actually, I'll let other people ask questions and I'll come back with some other ones. But is there an electromagnetic analog to this problem?
I like that question very much. So there's definitely an electromagnetic analog of linearized Kerr. which is this so-called root Kerr solution. Okay, very briefly, I'm just going to say I wanted to connect this to the world line action, but I'm just going to point, that's a way to write the linearized Kerr solution as a trace reverse metric perturbation. You might, and there's a nice way to connect that to linearized, to the exact Kerr solution in Kerr shield form. I'm just going to point at these formulae and ways to understand this in terms of Boyer-Lindquist coordinates. But okay, in this electromagnetic analog, so-called the square root of Kerr, we have a gauge field that very much is also representing a naked singularity. It's a spinning thing, naked ring singularity. It looks in so many ways very much just like the square root of this linearized Kerr thing. Okay, now your question. So we want to, on the gravity side, we want to perturb Kerr or maybe a naked ring singularity Kerr thing. And we have physics for that. I mean, like in the case of the Tucholsky equation, we know the physics. Like at least when it's a real black hole, outside it's the Tucholsky equation. Okay. If we had flat space-time, but we have a stationary solution for an electromagnetic field in flat space-time, which is this root Kerr thing. But do we have physics that would tell us how to perturb that thing? And basically, yeah, my answer is I don't know of any such physics, except, okay, one possibility. Okay, so you have the Kerr-Newman solution with charge and mass or gravity. So you could imagine, and you can write down like equations for electromagnetic and gravitational perturbations of that thing. This is all definite. And again, when there's a horizon, when it's actually a black hole, there's also a physical boundary condition there, and you don't have to worry about what's happening behind the horizon at singularity. Okay, you could imagine taking that problem and turning off gravity, and then maybe you get some equation that describes electromagnetic perturbations of your root Kerr naked ring singularity. That's the only possibility I can think of for giving some physics to this, getting some physics from somewhere for this root Kerr solution. Sorry? Okay. Would you like to elaborate?
So, I mean, in a double copy story, the amplitude associated with Kerr, the thing that you want to double copy to Kerr would be a Yang-Mills amplitude.
Yeah.
So it'll have intermediate, Yang-Mills vertices and whatnot. The 3-point function of Yang-Mills will be in. So you don't want to do it in electrodynamics.
Okay. But then what I said goes out the window unless you have a Yang-Mills charged, a colored. Yeah. That is the question. And yeah, so spin one, the spin one Tucholsky equation though is a vector field living on a Kerr background. And by Kerr, I mean gravitational background. But the direct analog would be like equations for electromagnetic perturbations of this root Kerr solution, which is just itself an electromagnetic solution in flat spacetime.
So
Or
sorry,
Yang-Mills.
the root Kerr could be embedded in Yang-Mills theory.
Okay. Yeah.
So that would be, so before you put in any perturbations, you just have a root Kerr, but you'd be sticking it in Yang-Mills. Then you'd scatter waves off it in Yang-Mills theory. It would be the perturbations of that thing.
But what equation? What?
There'd be a perturbative solution to Yang-Mills equations.
Yeah, but this Yang-Mills solution, it has some source.
Yeah, the source would be the root Kerr source.
This ring disk thing.
Yeah.
Right? We know what is the solution when it's just sitting there.
Yeah.
We don't know of any physics that describes how that thing.
But you know the source, so you put in the source and then you perturb the source.
Yeah, but what is the dynamics of the source? Where does that come from? I mean, okay, you could imagine there's some action that describes it. But what is that action? We have no idea. Okay, to linear order, we know. Yeah.
If it's just a solution of the Yang-Mills equations, there's no source. Just like in Kerr, there's really no source, right? You just have a solution of Einstein's
I
equation.
mean, in Kerr, I would say there is a source in a way. It is hidden behind the horizon, but there's singularity, but it is there.
Okay, but you don't need to know its dynamics because it's described by Einstein's equation.
Yeah,
right?
and you
So-
don't need to know the dynamics of the singularity because of the horizon. It doesn't matter. But if it's naked, yeah.
Well, I mean, presumably you have the same situation as in an electromagnetic case. You just specify a singular source which is charged,
Yeah,
right? And we have no problem writing down a Coulomb field from a singular point charge
yeah,
or a ring.
yeah.
And so I think Donald's suggestion is go to Yang-Mills where the equations are nonlinear and therefore you
Yeah.
can get something non-trivial out of a perturbation approach. Imagine you have a ring, disk, whatever, color singularity. This now generates the Yang-Mills field, which will look like this, and then you perturb that solution using the Yang-Mills field equations, and you'll end up with linearized Yang-Mills field equations around this, color field or whatever field sourced by some singular charge,
Yeah.
which you leave fixed. That's the
You
suggestion.
leave fixed that singular source.
Yeah,
That cannot possibly be the right answer.
but
That
you're
source-
leaving the Kerr source fixed, certainly, because you're leaving the background unchanged, and then you're calculating the linearized wave equations on that background, leaving the Kerr source unchanged.
Yeah,
as
but
a
that's
baseline
why
solution.
that Kerr is special. Gravity is special in this sense, I would say. In the physical problem where there is a horizon, right? You solve for gravitational perturbations of this gravitational background.
Yep.
So I would argue that singularity, in that case, that singularity behind the horizon, it is responding. It does have some dynamics, but magically here, we don't need to worry about it because it's hidden behind the horizon and information flows never out of the horizon.
Well, by definition, the equations you're solving,
Yeah.
right, the perturbation equations, are leaving the background unchanged.
Yeah, but
So you're not having the source respond.
It's like
The-
perturbing a neutron star. Need the fluid equations of the neutron star.
No,
Yeah.
you could need that, but that would be a separate, so then that's a different problem. Then you're saying you want to have a Lagrangian which both describes the source degrees of freedom and the field degrees of freedom, and now you have some coupled equations, source and then you want to solve those. But I'm saying when you solve the Tucholsky equation, that's certainly not what's happening.
Yes, but I would also say that, again, this is, you're getting lucky. Those perturbations that you solve for, they are encoding the response
I
of
should
that
do that.
source. Yeah, go ahead.
So this is a different question. It's about these logs and
Yeah.
diagamma. So is it obvious that your solution to the Tucholsky equation has to be matched by a tree-level Compton amplitude?
Well, that was our dream, to pick out tree level linear in G, but all orders in spin part, which makes sense up to fourth order in spin, but maybe not beyond. Okay, but we can also calculate, all of these terms, higher orders in G. They come out of the Tucholsky solution, no problem. They correspond to, I would say, loop corrections to the Compton amplitude. And so your question is,
Well, you have a GM omega to the 6 in
Yeah.
front of all of those transcendental functions.
yes,
So is it obvious that that can only, there's powers of G inside of the log, so I would
Yes.
say probably not. But you're solving non-linearly in G and expanding afterwards.
that's right.
So alternatively, you could try to solve things in perturbations of the, not perturbations of the background, but perturbations of the background expanded in G, which should be simpler. And that definitely, we know, for instance, which diagrams correspond to each power in the metric.
Right.
So it might be easier to see what's tree, what's loop, if instead of solving to all orders in G, and then at the end of the day expanding.
Okay. I'm totally with you. Like, instead of first solving Tucholsky to all orders and then expanding, can we go back to Tucholsky itself or the equations that are supposed to govern the thing and expand in G there?
Yeah.
Okay. that is absolutely something we've always wondered about. But you again run into weird things. So I go back to even just Kerr, as we said. Before we perturb Kerr, let's take Kerr, expand in G. Okay. Something very critical happens at the first step. We lose that horizon, right? So if I go to linearized Kerr, linearized in G, I'm already naked singularity, no more horizon.
Yeah. But in the amplitudes, you never see the horizon, right?
That's right. I agree.
pointed out.
And yeah, and it's quite clear that the amplitudes picture is the naked singularity thing for sure. Yes. But now we again have the problem of what are my boundary conditions for my perturbations at this naked singularity?
Okay, unless there's one more pressing question. Oh, you want to ask the last one? A little bit over time, right?
So I have a related question to this, like how to see the spurious pole can be matched to the amplitude, because I was thinking the physical pole is like when B equals to A, like in the amplitude story. Is that what you're saying? And then the spurious pole is like the VB equals to A. Is that what you're saying?
So you wanted to look at this scattering, the pole in the scattering angle formula or in the Compton?
Both,
Okay.
because you are talking about this spurious pole happen at the order A5, and
Yes.
then when you expand it in your way, it's a logarithmic, so I don't know whether I can interpret it as a spurious pole. So I just want to know, can I match?
Okay, let me look at the one in the Compton, like as an amplitude. Amplitudes people know, I guess, and tell me that poles of amplitudes must correspond to physical factorization channels, also internal particles going on shell. Okay, and I kind of actually, there are 3 physical poles of this amplitude corresponding to like the S, T, and U channels going on shell, if you will. But this is like a fourth independent, kinematically independent thing. We should never have that in the denominator. Otherwise, the amplitude is unphysical, because this does not correspond to any physical.
So it's not the VB equals to A pole you're talking about.
So I was just saying, so you take this Compton amplitude, you do something to it, you get this classical aligned spin scattering angle. There is another, I have no idea what to say about this one. I've always wondered what is that thing, but again, in the extrapolation of this formula to 5th order and beyond, something that didn't used to be in the denominator goes into the denominator. What does that mean? I have no idea, but it's a direct, it comes directly from this, the pole and the amplitude, I would say. I have no idea physically how to interpret that on the classical side.
Okay, I think we should
Yep.
close the session. Thanks, Justin, once more.